Hi, welcome to Dr. Pat TV. We're looking at linear functions. We're looking at those straight lines. We're looking at slopes, y-intercepts, difference patterns, gradients, all kinds of fun stuff like that. So we'll be talking about this. So let's look at an example. I've got a graph here from USA Today. They've got them on their front pages of each of their sections. Kind of really cool little visuals about information that they collect. So I'm looking at the average number of presents that holiday shoppers say they'll buy. And they did a little survey just kind of tabulating these things throughout the years. So the question is this a linear situation? Can we make a formula of a line that goes through these data points really nicely? One way to tell if something is a linear situation is just to make the graph. So take each of those data points, and we got the data point 2007, 23, and so that's what I've got, that data point. So I made a graph of each of the data points, connected them with a straight line like that. And so the question is, does this follow a linear pattern? And as you can see, these connected lines, it's not one single straight line. So mathematically speaking, as a true mathematician in that way, is this an equation of a line? Can an equation of a line be able to make a line that goes through these 4 points exactly? And I'd have to say no. Realistically, when you're looking at business situations out there in the real life, we probably say, well, an equation of a line, they don't all fall on the same line, but it's kind of close to being looking like a straight line. No other pattern that we can say. Then we would use a line to model the situation as an approximation, as an estimation. So even though in real life things don't come out cleanly, we do use models of linears just in case, just for estimations. All right. So another way to determine whether this is a linear situation is to look at how things change. Okay, so we're going from year to year and we're looking at the presents. So we want to look at the change in values. And I'm talking about these Y values, the number of presents. And so between 2007 2008, we had a change of 1.6 presents. Ooh, that's a negative. It went down. And also we got a negative change of 3.3 presents. So we went down again. But notice this change is not the same. And then between 2009 2010, we went down another 2.4 presents. So over these gaps of 3-year period of time here, between 2007 and 2010, that 3-year period, we had decreases, but they weren't of the same amount. And so in a linear situation, we'd be expecting to see these numbers exactly the same or very, very close to being the same. So now, you as a person who's using the math in the real world, you're going to have to make a decision. Do you say, well, context-wise, these 3 numbers are pretty close to being the same value, or context-wise, these are completely different values? You have to make that decision. If you feel that they're closely about the same values, then you can use a linear model. If you feel these 3 values are distinctly different, then a linear model may not be the way you want to go. All right, so not a true linear situation if I'm looking at it in the pure mathematical sense of what a line is, and that would be consistent same change all the way through. So let's take a look at a true linear situation. Salaries. The amount that you get paid per hour as you're working throughout the week. So if you're working 10 hours, you get 180 bucks. If you work 15 hours, you get 270, and so on and so on. So is this a linear situation? Well, what we can do is look at the change in the salary. Excuse me. We can look at the change in the Y values here, the salary, and we're seeing a consistent change of $90. So we've got the same change in hours, 5-hour change. That's got to be key. So if I went from 10 to 16 and then 16 to 20, I wouldn't have the same amount. I'd have to be careful. But as long as these are the same increment, 5-hour increments, then these changes make sense for us. So we're looking at 90, the same amount of change. That's a linear situation. So the change is the same amount. We have a linear situation. And then we're able to make our predictions for the 30 hours. We just add another 90 and then we can use that. So this is what we do in the real life. You take a table of data, a little bit more involved, a more complex situation. You're kind of looking at how things change in that table of data, so that way you can go to their end and you can make a prediction, because that's what we all want to do. We want to be able to make good predictions. If you can make good predictions, stock market is yours for the taking then. But quite an involved thing. You'd make your billions. Okay, so then what are we looking for? Our hourly pay. So that's a nice straightforward question. How much do we get paid per hour? Well, what we'd have is a nice 90 divided by 5. I would take the salary and divide it by the 5-hour increment, the change. So I'm looking at the change in hours and the change in salary. And so that would be 90 over 5 would give me 18. 18 would be my hourly pay. And that makes sense, because if I take 18 times that 30 over there for the total number of hours here, we would get 540. So basically what I'm trying to do here is illustrate this idea that when we're looking at change for linear situations, we want the change to be the same amount. And also when we do the change in the salary over the change in the time frame, then we basically have slope. We have an hourly rate. We have a rate of change. Slope is another idea of rate of change. And so change of our salary, the output, over the change of hours, the input, and that gives us our rate of change. Okay, that's the start of our linear functions. We'll do some more in the next video.